All right. All right. Now, for the beginning of the lecture, what we want to establish is what exactly it is that we are studying. All right. So control theory is the name of the course. The name is not completely self-explanatory. So let us at least give it a little bit of motivation with the emphasis of what we are going to do, not the general subject area. So first is just to explain to you, and 1 minute, let me do this. Okay. So what is control theory for, right? And you can, while there are many ways to talk about what control theory does, there are a few very obvious areas of application. One is industrial automation. That has been around for decades and decades, arguably for a century at least. The idea is that what we are going to study is directly applicable to automating production processes, chemical processes, things that happen in the factory, right, in the industrial sites. So as you can probably imagine, automation is one of the keys of success for modern production. And automation is only increasing in pace and in scope compared to previous years. Like we automate more and more, and the requirements for understanding how to automate is those requirements are high, and the necessity for them are large. So learning what we are going to learn is going to be basically a prerequisite to understand what's going on with automation in industrial facilities. Also, a relatively newcomer on the block is autonomous vehicles. That is quite obviously also a realm for control theory. If you want to design or control or do applications with aerial vehicles like drones or autonomous cars, autonomous taxis, self-driving cars, those autopilots for regular cars. I didn't put it here, but also there's all kinds of autonomous vehicles which are less obvious, like underwater inspection robots, pipeline inspection robots, robots that are specific, delivery robots right now, they're getting more and more popular. I'm talking about those small bots that you maybe see in the city delivering packages, right? All of this obvious application for control theory. Relatively new, but requires understanding of control to design. So, a lot of opportunities there. Now, less obvious, but nonetheless a key area is aerospace. Modern airplanes and everything that is somewhat related to aviation requires in the design, in the engineering, understanding of control theory. Same with anything related to space launch, anything related to vehicles designed for orbital flight or anything like that. You need to understand control theory for that. While this is a gigantic job market right now, so I understand that this might be very interesting for you. And this is obviously had always been a gigantic job market, and in general, industry, it's like almost everything, right? But this is nonetheless, I think, quite interesting. A lot of challenges, a lot of ideas that have been around for us control engineers have been coming from aerospace. It's an interesting thing. All of this is just broad areas. And if, anything has been taught to us by the, appearance of this gigantic block of new things, is that we can expect more. We can expect more. So in 10 years, 20 years, it is possible we would have a new type of technology which would be uh, requiring understanding of how to control it, right? So we may very well find ourselves in a world where there's something new, but the knowledge is still control theory knowledge. Control theory knowledge does not change as fast as new technology appear, but it stays relevant. So one of the key ideas that we will learn in the course have to do with Lyapunov stability theory, which was invented, formulated more than a century ago, and is still relevant. So the knowledge that we are getting here is not going to be outdated. In fact, it's going to stay more or less relevant, I think, for your whole career. But the application areas may update. So that's, I think, what's going to happen. Now, control theory, what you can think of it as is the science of is the science of how to make things move, right? That is, of course, mechanical engineering perspective on this, right? Electrical engineer or chemist both have a different idea of what control theory is. But for us, for mechanical engineers, it is somehow a science of how to make things move. So when you see something artificial moving in a controlled way, right? So deliberately getting from one point to another, or deliberately performing operation, washing machine, washing your clothes, that is a motion, it is deliberate. You can be sure that behind this, there is a control theory, right? So control theoretic knowledge is behind that. So if you are asking yourself, where do I apply control theory, where it is needed, look at anything artificial that moves in a deliberate way. That would be where you can apply it. All right. All right. So that is the if you want motivation. Now, for us specifically, what we want to do is in this course is in broad strokes, like in philosophical perspective, we want to learn how to think about objects that we can control, right? So right now I can tell you, okay, we have a truck, we want to automate it. I'm not sure if you have a clear picture of what is it about the truck that we are automating, what exactly it means, right? Or like how the truck is going to enter into our, design process. This might be a little nebulous. Our hope for this course is to make it less nebulous, more obvious what exactly we mean by this object, truck, being it, or airplane, anything. Right? Now, the other goal is the other thing we want to learn is to understand what kind of goals we can expect to achieve in control. Obviously, there would be things that are impossible, right? And there would be things that don't make a lot of sense. There would be things that are not practical, right? We want to understand what things do make sense, what things we should pose as goals, what things we should try to aim for, right? If you think about it, it's not obvious, right? Broad sort of like purposes are clear, right? You want autonomous car to get you from point A to point B. That is clear. But what about intermediate objectives? How exactly do you measure success of your control system in a particular instance of its work, right? It's not enough to just get from point A to point B. You also may say, okay, this car was unstable on the road. This car behaves strangely. This car started to oscillate somehow with increasing frequency of like increasing amplitude of oscillation. It was going more and more oscillatory, right? I'm simplifying here, but you can get the idea, right? There are things other than just fulfilling the task. And in fact, even fulfilling the task once doesn't cut it. You also want to always fulfill the task, right? So there is statistical aspect to it and so on. In this course, we will discuss this, right? Obviously, we'll discuss how to do it, right? Not only, not only what to expect, but also how, That is a big part of the course. We would explain how to control. And we would explain problems that we face when working with control. Those, again, are not completely obvious. We will make them obvious, you would understand them, and we will learn how to deal with those problems. Okay. This is still introductory course, right? So what we want to do here is allow you to have enough knowledge to study advanced courses later. What advanced courses depends on you. If you're going to work with autonomous vehicles, you would go to there. If you want to go with advanced industrial automation, maybe you get nonlinear control. If you go for bipedal robotics, you would get courses related to that. Possible that you would get master degree, a PhD. The number of courses, the number of studies you can take is gigantic. But control theory is a prerequisite for a lot of them. So we would aim to clear more or less all prerequisites that that I expected from an introductory course. Okay. Now let me see if I have anything. Right. For today, what we are going to do is to just get one aspect of control theory. We would start the next slide. We are going to have actual mathematical study, just to motivate it a little bit. The objects that we control, right, that we can control, often described using differential equations, ODEs, ordinary differential equations. Right? Now, for today, our goal is to understand one way to represent ordinary differential equations, and that is in state space form. I would explain this in the rest of the lecture. That's what we are going to spend our time on. Now, if you have any questions about introduction or motivation, I'll be happy to answer. Okay. Just a reminder, at any time, you can interrupt me, stop me, just unmute and speak. I will be happy to explain. I'm going relatively fast, and I don't always pause to ask you for questions. But I'm hoping you would just speak when you have a question, and I would stop and we'll discuss. All right, good. Now begins the mathematical part. This course, if you did not expect, hopefully you did, is a mathematical course. In many ways, it will be full of mathematics. That is the nature of control theory. Control theory, in a sense, could be seen as a branch of differential equations theory, right? We're not going to treat it as such, but it is very mathematical. So please be prepared to learn a lot of mathematics. But for now, let us just recap. So we have first order ordinary differential equation, which can be written in this form. Right? Let us pause here and not rush and understand what we are seeing. So first of all, what do you mean by first order? It means that the derivative is a single derivative here in the equation. We don't have double derivatives like second derivatives, third derivatives, nothing like that. First order equation means there are only first derivatives in the variables, right? Now, what do we mean by normal form? Normal form means that higher derivative is on the left, everything else is on the right. That is all. That's normal form. Why ordinary differential equation? Well, that is just to differentiate them from partial differential equations. We will never see them in this course, so all our differential equations will be ordinary. Theoretically, we could drop this O because we're never going to see PDEs. but it is a very standard way of saying it, ODE, so much so that the word ODE is almost a noun for us. So we don't want to drop the O. So we would always use ODE to describe our differential equations. All right. Now let us study this differential equation a little bit carefully. This equation has a x on the left, function of x dot on the left, sorry, function of x and t on the right. Now x, if we describe it as x of t, is a solution to this differential equation. So x itself is somehow a variable of this equation, right? T is what we call a free variable. It is a scalar. We can call it time, right? We can call it time. For us in control, almost always it would mean time. It doesn't have to be, but that's the most typical interpretation. Mhm. Now, just to reiterate, so x is a function of t, right? T is just a free variable. It's not a function of anything. X can be a scalar, can be a vector, right? T is always a scalar. All right. Now, there is another way to describe this thing, and that is we can call it a dynamical system, right? Why dynamical? Because its variable changes with time. Its variable, by that I mean x, right? So it changes with time. And x, instead of calling it a variable, we can call it state of the dynamical system. We can call it a state, right? So dynamical system is a system whose state changes with time, right? Why does it make sense to use such a strange terminology? Well, imagine we have a dynamical system, which is a petri dish with bacteria. Number of bacteria is our state, right? Number of bacteria is our state. And with time, the number of bacteria changes, right? That would make it a dynamical system, as opposed to static system where nothing changes, right? In a dynamical system, number of bacteria changes, okay? And you can see the difference between time and x very clearly in this example. Time is just, time in which things evolve. State can be a number of bacteria, or it could be, for example, number and position of bacteria. That would be crazy to measure position of each bacteria, but one could imagine. Or the state could be number of two different bacteria species, right? So there will be two different variables: number of bacteria A, number of bacteria B. Right? Time is always a scalar. It's always just one time. Right? Okay, let's get some simple examples, mathematical examples of this equation. Here is one example. X dot equals to minus 2x. As you can see, the highest derivative is on the left. Here is a state. In this case, it is scalar. You can tell it is scalar because I would use bold to notate vectors and a regular font to notate scalars, a regular italic to notate scalars. In this case, this is scalar. So this is a very simple ordinary differential equation. All right. Do we have questions about this part? As I apologize about the background noise. There might be a little bit. Hopefully it's cancelled, but if no, I apologize. All right. Now, a few words about state. A few words about state. State of a dynamical system is a minimal set of variables that describe the system in a sense that knowing the current state and all future inputs, you can predict how the system will behave. Right? What do I mean by that? Well, if you have a system, you can you don't want to call just anything its state, right? You want to know enough information to predict how a system will behave going forward, right? When we say predict going forward, we mean, of course, that we want to predict something in particular. For example, if it is a car, and you want to predict maybe its position and velocity into the future, right? Given how much you press the gas pedal. So the state of the car would include, most likely, current position and velocity, right? If you don't know its current position, you cannot predict its future positions. So if you care about position of the car at all, you have to include it in the state. If you don't have to. Right? It depends on the task. So it depends on the task. So a couple examples. For a spring damper, that is hopefully familiar system. All of you know what spring damper is, right? Correct? Wait, suspension, right? Like this. I'm sorry for my cartoon. Right? Like the damper, right? Something that really dissipates energy, and there is a spring element. I'll draw it like this. It's a little bit hard to draw on Zoom, so my apologies for the quality. Right? So spring damper, right? A spring and a damper in parallel. For spring damper, the state would be position velocity of the mass, so of whatever it is that we are trying to damp. If we have a mass here at the end of spring damper, its position velocity would be state variables. For double pendulum, state variables may include joint angles and joint velocities. Right? So, for example, for Kuka arm, state variables may include each joint position, so orientation of in the joint, right? Joint angle, and velocity of each joint. That will be the state of robot Kuka. For a flying robot, the state might be position of the robot, orientation of the robot, linear velocity of the robot, and angular velocity of the robot. Right? So for a flying robot, for airplane, and so on, that might be a state of the system. Does this make some sense?
Yes.
Okay, good. Later, I would recommend you to like if at some point you feel like, okay, I'm not sure if this makes sense, you can go back and think about it one more time about the slide. After we study a little bit more application for this terminology, over time, what we are trying to do will become clear. Then, when you understand what we are trying to do, it will be easier to understand this like philosophical description here, right? So in case right now it is like 50% clear, later come back after we did a couple lectures using this terminology, then I think it will become clear. Okay. Now, we were discussing first order ODEs. Let us describe a little bit higher order ODEs. So nth order ordinary differential equation looks something like this. E nth derivative, right? Derivative in this case, in this lectures, we will describe in this upper index with normal brackets, right? That would be the derivative of nth order. Well, it is a function of y taken to the derivative of n-1 order, n-2 order, all the way to the first derivative, zero derivative, and eventually time, right? So this is how we describe nth order ordinary differential equation. Here, I don't use bold, so x here is a scalar, and y here is a scalar, and all of those are scalars. And f is a function that maps scalars to scalars. Okay. Now here, y equal y of t is a solution to this equation. Let me remind you what solution means mathematically. If we substitute y into this whole, system, so here we substitute y, here we differentiate y and substitute it. Here we differentiate y n minus 2 times, differentiate y n minus 1 times, differentiate y n times. We put it into this function. This equation becomes equality, right? So it was equation, it becomes equality. That's what it means to be a solution. All right. So it is a dynamical system as before. There is the state of the system evolves with time. But what constitutes the state is not as obvious. So in this case, what we would propose to call a state is y dot, y double dot, y triple dot, all the way to y minus n minus 1 dot. Let us understand the logic of it. The way the highest derivative evolves through time depends on all of these variables, right? So we're going to use all these variables that I highlighted as a state because the highest derivative depends on them, right? Highest derivative itself is not independent. It is completely dependent on all of those. So including highest derivative in the state makes no sense. It simply depends on other variables. But other variables, they don't necessarily depend on each other. Because given different initial conditions, they can, first of all, you would think that position depends on velocity, right? Because you integrate velocity to get position. But get different initial condition, and given the same velocity profile, you would have a different position profile. So they're not dependent, they are independent. Velocity does not depend on position. Position does not depend on velocity, not completely, right? There's a question of initial conditions. So those variables are independent, and they form a state of the system, right? That's our logic. Now consider a physical example. Here's a pendulum. Here's a dissipative term. So dissipation happens with 0.1, right? That's how fast the energy dissipates in a sense, right? You can say this is a viscosity coefficient, normalized by the mass of the pendulum. And here is a gravity term. Now here the state would be y dot and y, right? Y can be orientation of the pendulum. Y dot can be angular velocity of the pendulum. So that will be the state. Another example, DC motor with a constant voltage, right? Here, there's the equation. I don't need to read it out. It's quite clear. It's a system of two equations, right? Now, Y1 can be current here, right? So this part would be a part related to resistance, right? Current times resistance is drop in voltage, right? Here's the outside voltage. Here is a resistance related to back EMF. This is angular acceleration of the shaft, angular velocity of the shaft. And here is the current multiplied by torque coefficient, giving you torque, right? All of this is, you just have to sort of like believe me or whatever, that this is a description of DC motor. I think you probably studied this on the mechatronic course, so this should not be completely new to you. where you will study at mechatronic course. That I'm not sure if the mechatronic course is after or before this one. Did you already have mechatronics in your curriculum?
No, it's next year.
Next year. All right. So that's where you're going to study all of this. So please don't worry that we show it here as a mathematical object. I think it is quite clear, right? As a mathematical object, it's quite clear. Now, let us test how clear our definition of the state is. Like here, it shouldn't be completely obvious what the state of the system is, right? But let us try. Like this should be a state, right? It is independent variable, it's not the highest order derivative, right? Right. So this variable is a state. Should this variable be a state? It is first derivative. There is a derivative higher than that. So it should be a state. Yeah, indeed it is. It is a state of the robot, of the system. Here it is again. So all of those are state variables, y1, y2 dot. Now we could, or if we wanted, we could include y without a dot as also a state variable, but we don't have to. It is our choice. Do we include it? Do we not include it? It's our choice. Those two clearly are not state variables here because they depend on other variables. So they're not state. We don't have to include them. All of this may sound a little bit, like there is some kind of rule which is not completely explained. Good news for you. This is not something that you have to sort of do as an exercise or, that is not the integral part of the course. I'm more giving you just a sort of idea of what the word state means. You don't have to memorize it. Doesn't matter. Later in life, if you dive deep into control theory, you would see discussions of this topic for serious reasons, right? But for this course, this is not very important to understand how to decide which variable is a state. But it is good to have a feeling for it, right? And I think the feeling that this is not a state, but every variable here, which is not the same one as here, is a state. Yeah, that's a good feeling, right? It makes sense. All right. Now we will get closer to what we actually want to do, right? A system of first order linear differential equations. Now, for the first time, we see this word in this course, this word linear. Linear is a requirement that your equations, the variables of your equations, appear only linearly, right? So, for example, this is a linear equation, system of linear equations. You can see that x1 appears linearly. So it is multiplied by a constant, and it is added to the sum total on the right. Another part, there's x2 appears linearly, multiplied by a constant. There is no multiplication of variables, no square roots, no trigonometric functions involving variables. That is what makes ODE linear, right? So they would always have this form. Constant times x1 plus constant times x2 plus constant times x3 and so on and so forth. That is what makes a linear ODE. In the normal form, derivatives will be on the left-hand side, everything else on the right-hand side. And that is what we are going to see throughout the course. Just to make sure you understand the implication of it being linear, let's go back for a second and look at this equation. This is not linear because we have sine of y. So this is not linear, right? But this is linear. Like, we have variable multiplied by constant plus variable multiplied by constant plus a constant, that's acceptable. This would make it technically a fine equation or non-homogeneous linear equation, but we're not going to go into those technicalities. For us, this is acceptable. This is still a linear equation. Same here, constant times variable, constant times variable. So this is linear, this is not linear. All right. If there was x squared, wouldn't be linear. If there was x1 times x2, wouldn't be linear. But all of this is linear. All right. Now, for us, why we spend time on this is almost everything in this course will deal with linear equations specifically. A lot of the results depends on them being linear. So that will be important. I'm not going to stress it too much now, but as we go forward, I will, you'll understand this better and better. The importance of linearity. Right. Now, one thing that we can stress right now is that linear equations can be represented in this form if they are homogeneous, meaning if there is no constants or anything else hanging at the back. That is how a linear system of linear ODE differential equations look like, can be represented like. Right? X dot equals to AX. Why can it be represented this way? And I'm saying any first order system of linear differential equations in the normal form, homogeneous, can be represented this way. Why? Well, here's the example, right? We have derivatives on the left-hand side. Let's just compare. Derivative on the left-hand side, same as here. Here, though, we have this two equations with a lot of sums and so on. Can we always represent it this way? Well, indeed we can, because this can be written like this, you see? So let me use a different color. So we take our variables, x1, put them into a first part of this state vector, what we will call it. And those variables would multiply, minus 20 and 10, the first column of this matrix, right? We take next variable, x2, put it as a second element of the state matrix. It would multiply the second column of this matrix, right? You can always do. You can always do this. You can always change a system of linear equations into a matrix of coefficients times a vector of variables, right? I think this operation is quite clear. I don't need to explain it more. Or what do you think? Is there questions about it? This is one of those moments where it is good if it is unclear, it's good to spend time on this. No? All right. So we would always be able to write our linear equations in this form. It would always be possible, right? If it is a system of first order linear differential equations. Now, let us consider linear equations, but now of the nth order. Oh, here's an example. Please just spend a second looking at it. I think one feature that you might notice is that highest order derivative is on the left-hand side, as usual, but it is now multiplied, and there is a whole lot of other stuff. Everything on the left-hand side. So this is not a normal form. This is not a normal form, right? I'm not sure what the name for this form, but that just a typical form of
It's
writing.
general.
General form.
They call
Okay.
it, yeah, general form.
Good. General form of a differential equation, right? So you can see there is a difference between everything that we saw before and this. Here's just a couple examples, right? Why do we introduce this form? Well, simply because this is how typically they are written. Like when you actually encounter this equation in the wild, that is what you're going to see. Not normal form, but this form, right? General form. For good or for bad, that is what we are going to see. So here it is. Now let us. Okay. Right. So what we saw so far, two forms. Let me show. This form, equation 6, and this form, equation 9, right? Those are basically our main guests here. Those are the equations with which we're going to work. In terms of, differential equation aspect of it, those are our two subjects, right? We're going to spend a lot of time working specifically with them. But it is not enough for control theory to consider equations in this form and in this form. Not because of the differential equation aspect, but for a slightly different reason. So I will continue a little bit and would give you like additional information. But for now, just keep in mind that this and this are our main subjects. So linear, the differential equations, and represented in this way or this way. Okay, moving on. Next subtopic. Sometimes we want to consider differential equations, but with an input, all right? With an input. So here you can see there is a difference between what we saw previously and what we're seeing now in the form of this u of t function. So this u of t is a function of time. It appears in this like general form of this differential equation on the right-hand side, all right? On the right-hand side. What does it mean? Well, it can mean many things, right? For example, it can mean control input. So for example, voltage or torque, right? That we can directly control. So stuff that we put into our system. If our system is a motor, U of t can be voltage. If our system is a robot arm with a torque control, it can be torque. If it is a flying quadrotor, it can be angular velocity of the rotors, or anything else. It depends on the abstraction level in the control system. So it can be control input, right? It can also be external forces, right? External forces. So for example, it can be wind acting on your airplane or on your flying robot. Can be what should I say? The force from the environment acting on your pick and place robot arm. So sometimes the input is not what we control, it is what someone else controls, like what environment gives us. And also it can be just something we do for a test, right? For example, we can ask, how would this differential equation react if the input was a step function? So instantaneous change of input. Or what would happen if it is a sine wave, right? So in this case, it doesn't really matter if we are modeling external force or if we are modeling control input. What we care about is how the system behaves when this is put through it. Like, you're putting a sine wave through the system. How would it behave? How it would react? That is also
May I ask a question?
Yeah, go ahead, please.
About this control input. So it should not depend on the state of the system. So it only can depend on time.
Yes. In this case, when we let me be careful. All right. Later in the course, we will discuss control law, which would depend indeed on the state. Right. Here, so this is
so just like prerequisite dummy control input that depends only on time.
I would recommend. So this is a good question. The only problem with it, it is very philosophical. So I would, if I attempt to, sort of honestly answer it, we'll go into very deep forest. So if you allow me, I would just say that for now, we're thinking of it as a function of time, just so not to confuse the right-hand side and the left-hand side of the equation, right? But late in the course, we would come up with control law, which would depend on the state. But I think there would be no confusion. So, just for now, for this lecture, let us together think of u of t as a function of time. I think,
Thanks.
yeah, within like 1 or 2 lectures, we will be able to explore more possibilities. Yeah. Yeah, but yeah, the question indeed is interesting. It's just that I try to avoid very very abstract discussions when we don't. Right. So yeah, for now U of t is a function of time, and this is what I can present. Okay. Now here is an example of ODE with an input, right? So you can see it is a first order ODE in the normal form, right? Linear. The only difference is that there is now this additional part here. And if u, for example, is equal to 10, I think it will be exactly the same example as we saw 2 slides ago. So u can be a constant, right? It doesn't even have to be a function of time. It can be a constant. So, all right. All right, right, right. The same exact example is written here. So you can see the only difference is that I changed the variable names. Maybe I should have changed them to here too. Maybe. But it is written in the state space form, in this form with a matrix times vector. Right? And one thing I want you to notice is that this plus u part appears like this. So u times 1 gives you, plus u in the upper equation. Nothing here is given by 0 times u. So this matrix form can handle the situation where one variable appears upstairs, another one does not, and it doesn't appear downstairs. This is how you handle it. Okay. Now, when we introduce input, we are almost there at the, having our equations the way we want them for our course. So there will be 2 types of equation. One is general form with the right-hand side. So general form in this right-hand side here. That is for higher order ODEs. And then we would have state space representation, right? State space representation. That's how it looks. Now, state space representation would be first order ODE. On the left-hand side, there will be a derivative of the state. On the right-hand side, we would have a state matrix A. We call it the state matrix, sorry, times state, plus control matrix U times control input U. I'm using here the words control matrix and control input only to give it some name. If it was, for example, disturbance input, we would call it a disturbance matrix and disturbance input. Right? But it is convenient to call them something. We can always just call it a B matrix. That is understandable. There is no problem with this at all. But often people would call it a control matrix, and this is a state matrix. Right? Now, we will always write B like this, like a big, like using capital letter, bold, simply because it is somehow a tradition. Even if U is a scalar, we would also always write it in bold, because it can be, in general, it can be a vector, And so much notation is built around using this type of representation that I would prefer not to always keep it like that, like to always present U using bold regular letter, B as a capital letter, and so on and so forth. So that is how we're going to do it. All right, and those two equations, they are our equations. They are going to be very important for our course. We are going to study how to control objects that can be represented by those equations. And as you already saw, what we can represent by those equations is a spring damper, a DC motor. That sounds like very specific, but during one of the lectures, I will show you that almost any robot can be represented by linear equations using something called linearization, right? So this is something you will study, and then your instruments will apply to almost anything. But for now, you can directly apply them to DC motor and the spring damper. They're naturally linear. Okay. One second. So having input is not the only thing that you can have. You can also have an output. That is maybe not surprising because of the way English words work, right? If you have input, maybe you should have an output. So let us understand what output means. So what it means depends on the particular use case, right? It's not related to mathematics of the problem. It is related to what we actually want. Right? For example, output can be what we measure. Like if there's a physical robot, there might be sensors, and we might want to measure something. So what we measure might be our output. So, you have a system, it is like a black box, but out comes a little bit of information. This information is our output. It can, on the other hand, be what we care about or what we want to control. For example, height of the quadrotor. Let's say you just want to film an event. What you care about is the height of the camera being constant, right? Okay. And maybe in this, like, as long as the camera doesn't move forward and backward too much, you don't really care about the position. Like the position is, roughly speaking, important, but as long as it doesn't move around, maybe you don't care, Like the position is, shifted by 10 centimeters from where you actually wanted your camera to be. On footage, it won't show. So maybe for you, that's fine. But the height might be very important for you. No, okay. So that might be another way to think about output. Output can be what you care about, right? Not necessarily what you measure. So output is traditionally described by a Y, letter Y, and it depends on the state of the system. It can also depend on the input, but that is a separate discussion. But it, I can say, always depends on the state, right? So what you measure should be the state of your system. What you care about should be state of your system, right? Not all the state, but at least some components of the state. Maybe a linear combination of those components, but it should have something to do with the state. All right. So let's get maybe a general form now. So this is finally, we arrived at a general form for this equation. Like we're not, for this course, this is like all we are going to need. Like we're not going to go any deeper into this, right? This upper part you already saw, that is our x dot equals to ax plus bu, our system of linear differential equations with input. This is just linear equations. That is not differential equation, just linear equations. Just says that y is, you can calculate it by multiplying x by matrix C. And that is all. That is all it says. So the first equation is differential equation. Second equation is just linear equation. All right. Now, if u and y both happen to be scalars, so they, they are scalar, not vectors, you can try to represent this whole thing, equation 17, as a single ODE. And indeed, it would look like this. Now, let me just point out interesting fact. See, y here is the same y as here, if it is scalar, right? If it is scalar. U here, same u as here, if it is scalar. So you can encode equation 17 in the form 18, as long as y and u are both scalars. If they're not scalars, obviously you have a bit of a problem, right? But if they are scalars, you can encode it like that. So somehow those two equations that we have been describing, this and this, are related. They're not mutually inconsistent. In many ways, equation 17 is slightly more general, but equation 18 is a particular instance of equation 17, you can say. Right? We would make it clear at the end. Let me just check how much time we have. Can you please update me? How much time do we have until the end of the lecture?
26 minutes.
Thank you so much. Okay, we have plenty of time. Right, we're actually going to finish early today. So in case you have questions, perfect time. All right. So those two questions, all right, they are related. Just keep it in mind. We will in a bit describe this relation. But now, just a little bit more terminology. So we will focus, as I said, on this type equations and this type equations. Right? If those two variables are scalars, then the system can be called single input, single output system. So SISO, that's what we call it. Single input, single output. Right? If they're vectors, on the other hand, it is multi-input, multi-output, so MIMO. Right? So if the system is single input, single output, we can go from here to here, to ODE. Right? If it is a multi-input, multi-output, it's not as clear how to do it. Right? But for single input, single output, it should be relatively clear. Right? Now, here's a question. Can we also go from this to this? That is an interesting question. Can we go from 19 to 20? That might be interesting. So let's look into it. Well, I will just give you an example. Consider this particular equation. So it is, as we say, general form. Right? On the left-hand side, we have this equation. On the right-hand side, this equation, this u. Now, what I propose we do is we make substitutions. So we define x1 as being equal to y. Right? We define x2 as being equal to y dot. We define x3 as being equal to y double dot. Right? Now let us understand what let us understand what derivatives of those variables are. So x1 dot is equal to y dot, which is x2. Okay. So notice x1 dot. Okay, let me be careful. X1 dot is equal to x2 because x1 is y. X1 dot is the y dot, which is x2. Right. So we have a relation between x1 between those two variables. In a similar way, x2 dot is equal to, one second. is equal to y double dot, which is x3. Right? So again, we have a relation between those two variables. x2 dot is equal to x3. Now x3 dot happens to be equal to y triple dot. And for that, we can for that variable, we can actually take this, like, y u here minus this whole thing here, right? Which can be expressed same as before, but now using all those, variables that we introduced. So, x1 instead of y, the x2 instead of y dot, and the x3 instead of y double dot. And somehow, we even for x3 dot, we get a relation between it and x's. So now let me just point out. Three derivatives of our x variables depend on x variables and an input, right? So we can write this in the matrix form. Here is the right-hand side from here, right? This is the same right-hand side. This green part, just one second, let me color code it. So this green part where x1 dot is equal to x2, that is, how we get it, okay? This part here where x2 dot is equal to x3, that is how we get it, right? And this last part, this last equation, I think it is obvious, right? Minus a0 here, minus a1 here, minus a2 here. And u, this last u, here it is. So if you just multiply and add all of this, you would get a system of equations 21, 22, 23. And you're done. Now, this trick allowed us to rewrite our original equation. Let me just get something. So this original equation into this state space form. This trick would work on any general form ODE. Of course, it might be bigger, but nothing changes. In fact, it would work on systems of ODEs. So it doesn't really depend on having only one ODE. It's just very typical to have one ODE for at least, for our purposes. For you who are robotics students, you may know that often what you have is a system of second order ODEs that come from like Laplace equation, Lagrange equations and Newton-Euler equations. There you can use the same trick. And in fact, you probably have seen those tricks, maybe. If not, just use this trick, that's all. You decide that velocities are half of the state, positions are half of the state. You substitute them, you get state space representation out of your manipulator equations or Lagrange equations or Newton-Euler equations. All right. So this trick is general. It would always work. And you can see it just one slide. It's very simple. You can always go from ODE to state space. Very convenient for us. Since we are going to do a lot of our control specifically in state space, this means that any task that is given to you in the form of ODE, you can solve it using state space solutions. In fact, you can go backwards too. It's just that I don't want to spend time on this. Like there will be automated tools. The techniques are a little bit more elaborate. And in practice, usually what you typically do is go from ODE to state space. So in case at some point, if you have to go from state space to ODE, either I can explain to you personally or, you can use automated tools for that. But this you have to do by hand, to know how to do by hand. And you can see this very easy. So we'll practice this. I believe you practice it with Valeria, and it should be also on assignment, this exercise. All right, let me just double check. Yeah. All right. So with this, the content for the first lecture is over. Next lectures, they will going to be a little bit longer and more involved, but the first one is relatively short. I will use this opportunity to kind of like explain to you how to interact with, with the course material, with GitHub page and everything. So, but we don't need to record this, so I'll just stop the recording.